Welcome, one and all, to video 8, the ITRC CDFA video series on fertigation. So this is video 8 of about 22, and glad to have you here. This one deals with nitrogen conversions. As always, we want to make sure that you know that there are resources available to back this up, because you're not going to get everything from these videos. And we have books on drip, microirrigation, fertigation, and lots of publications on our website. So please avail yourselves of that information. The videos that we have regarding lab exercises are here, and they're interesting. They're not in a lecture format, but they show you what happens in a lab exercise, sort of like being there, but not being there. So here's the context of this video right here, video number 8. It discusses, or I'm going to discuss, nitrogen transformations and processes really in the soil. And there really isn't anything super easy about this topic, but it should help you understand what happens to fertilizer when you apply fertilizer of different types. You know, how it's a little difficult to know what's going on, but you can get a pretty good idea. So let's get started here. First of all, there are different forms of nitrogen, as you know, found in fertilizers, and then different forms are used by the plants, and they're shifting around in the soil in terms of what their form is, depending on microbial action. We have a term, and this will be on the next slide, a term called a nitrogen cycle. And we have an image that depicts a wide variety of ways that nitrogen compounds exist and how they change in the soil and air. How the nitrogen might come into the soil from the air or leave from the soil into the air. So here's the nitrogen cycle sketch that you'll find in your book, the chapter on nitrogen. And there are all sorts of processes and a lot of different words. But this sketch tries to show you what's going on. There's something called fixation, and I'll go over all of these: volatilization, nitrification, denitrification, mineralization, immobilization, and leaching. And what you can see here is, let's just kind of take a look at it. On the upper left-hand side, it said fertilizers and rainfall. And so those are sources of various forms of nitrogen. Then on the upper right-hand side, there's cropped and grazed. And so there are various crops, and there's one in particular there on the far right, and that's called a legume, which I'll discuss. That's the only one that really fixes nitrogen from the air. And then down below, the nitrification and all that stuff, that has to do with down inside the soil. And if you notice, there's a lot of moving around and transformations. So I'll take care of these one at a time. First of all, there's this idea of fixation. Fixation is limited to legumes, and certainly in the United States, we typically think of a legume as alfalfa, let's say. Alfalfa really doesn't need nitrogen fertilizer. Now, if you do put nitrogen fertilizer on alfalfa, what we know is it's kind of not a technical term, but it's a lazy plant, and it'll take up the nitrogen fertilizer instead of fixing it from the air. But what happens, if you remember, the majority of air is nitrogen gas in N2, and N2 is not something that is a fertilizer itself. It has to be converted to ammonium, and that's what's done inside these legume plants. In other countries, you even find some trees that are grown for wood that also fix nitrogen from the air. It's kind of interesting. So what you have is these nodules down there in the roots that are able to use the nitrogen gas from the atmosphere. They convert it to ammonium, and then ammonium, of course, is converted to organic nitrogen in the plant tissue. Volatilization in this nitrogen cycle is demonstrated sort of near the upper left-hand side. It says ammonium volatilization. And so what you have is the ammonium ion. It's a cation, NH4. And when it's near the soil surface, it can convert to ammonia gas. That's NH3. And of course, that just goes into the atmosphere, and it's lost. So where does this occur? It occurs primarily in the high pH soils. You can see the reaction here. At the bottom of the text, there's ammonium plus a hydroxide ion, that's OH, and they get together and they make ammonia, that's NH3, and water. So anyway, that's the process, and it can move back and forth here depending on the pH. But if you have a lot of OH ions, in other words, if it's a basic soil, it drives the process to the right. I think this is a little table that isn't very familiar to most farmers. It's table 8.1 in the book, and it gives you a little idea of why farmers who inject ammonium in the form of aqua ammonia and anhydrous ammonia, they do this into high pH water. You can have significant ammonia losses through the process of volatilization. And then it's a similar thing that happens on the soil itself. So if you take a look, for example, a soil water pH of 8.2, that's not unusual at all. You could have about 10% volatilization. And anyway, and then on top of that, you can have, you know, these actions that I discussed earlier in another video where you get the calcium falling out of the water. And basically, bottom line here is you really need to take a look at what type of fertilizer you use when you're in these high pH situations. If you take a look at this in the center, the word nitrification has been circled. And nitrification is the biological process where there's conversion of ammonium to nitrate, or else urea to nitrate. The transformation of urea is done by an enzyme. It goes to ammonium first, and then there's a bacteria that converts the ammonium to nitrate. But this is typical. In other words, you put the ammonium in and urea in, and there's a conversion process, and most of it ends up eventually, with time, as nitrate. And that, as you recall from previous videos, is nitrate is found in the soil water, moves with the soil water, and it's easy for the plant roots to access it, therefore. Now this transformation, because it's the biological or actually microbiological process, really depends on things like availability of water and also temperature. And this little graph, this figure, just shows what happens with two different temperatures in the soil. And you see on the left, that one is a 75-degree Fahrenheit, and it shows that 100% of ammonium, that's NH4, that's in the soil, you put it in as fertilizer, it'll transform to nitrate within 2 weeks or so. Whereas if it's cooler, 50 degrees Fahrenheit, it may take 12 or 13 or 14 weeks to do 100%. So these are ballpark numbers. And as you know, the soil temperature is not consistent all the way with depth, but they give you an idea that the transformation is relatively slow in cool climates and relatively quick in warm climates. Denitrification is shown in the middle up near the top. There's a circle around the word denitrification. It's up near the soil surface. And that is up there because what it really illustrates is that you can get nitrogen that converts to, it shows nitrate there being converted to a gas. And that occurs, though, only in anaerobic conditions. In other words, conditions where the soil is saturated and there's no oxygen getting down there. If you do indeed have a soil that's saturated with no oxygen for a considerable amount of time, you're in deep trouble anyway, because the roots need oxygen, and field capacity is considerably has less moisture than saturation. So anyway, bottom line is, with good irrigation management, there should be few to no times really that you get these anaerobic conditions. So it's something we normally don't consider too much. Some people are concerned about this because of because what happens is you can get pollution through denitrification, but we're just going to move on with it here. The next process is mineralization. There's a circle down on the bottom. And what you can see is it sort of looks like roots uh, go down into this little picture, and then something comes out of it, and there's humus. Basically, what it is you have organic matter in the soil, decomposed roots, or maybe you put on manure or something like that. And the what you have is proteins inside the plant, and they break down. They break down with bacterial action and convert to ammonium. And then, of course, you have the process of going from ammonium, you get to nitrification, going to nitrate, and so on. And all of this is biological. And because it's biological, you saw the little graph, of how things vary depending on the temperature, just as an example. We know what happens, but it's a bit unpredictable and slow, this process here. So let's see, what's this mean, this process of mineralization? It's a bit slow. Well, it does have quite a bit to do with nitrogen management. We have a lot of encouragement, of course, to have healthy soils. After all these processes with nitrogen are microbiological. And we know that humus in the soil is good for soil structure. It's good for plants. We know the general ideas that incorporating a cover crop is great and everything. And there's a lot of interest in organic farming. And Hartz in 2010, a while back, did take a look at a variety of, let's call them organic possibilities. If I start on the top here, he tested liquid organic fertilizers. So these are ones that are sold, as liquid organic fertilizers. And he found that they rapidly produce plant available nitrogen. So that's good. Now, typical organic culture, and that's, where you have, the things you do with organic farming typically, aside from fertilizers, where you're mixing things in and waiting for decomposition. The bottom line is you don't rapidly obtain plant available nitrogen with that. You go to the next little box here, it says what he found is plant available nitrogen contribution from manure-based compost is often limited to less than 10% over a growing season. Wow, that's a little slow. And then the next box says, what if you have a cover crop? Which is a good idea. I'm not saying that any of these are bad. I'm just saying that it's difficult to know how quickly you get the conversion. And when you're trying to really nail the nitrogen concentration in the soil with the uptake and avoiding leaching, it gets a bit difficult. So the next to last box says less than 50% of the nitrogen developed by a cover crop is converted to plant available in a growing season. Now, certainly this has to depend on where you are, but this is the work that Hart showed. So basically he's saying, hey, look at, you might, well, what he says is take a look around and make some hard decisions here, but you can't depend on the manure and the compost to give you quick turnaround in a predictable fashion. So there's a little bit of mumbling around here about what to do. Now there's another concept. If you look sort of in the center bottom, the word immobilization is noted there, and it shows that somehow things go to humus or to mineralization. So let's see, what do we have here? Immobilization. What you get is ammonium and nitrate are in the water, and somehow they're grabbed by microbes in the soil, and the microbes temporarily tie them up. In other words, they're not available. And the classic case that people, agronomists, know about is the concept of a carbon-nitrogen ratio. That's a CN. If you have a high carbon-nitrogen ratio, and that's, for example, if you have straw in the field, wheat straw, rice straw, something like that, and you mix it in, this is not to say it's a bad thing, but what will happen is you end up with a shortage of available nitrogen as that stuff is being decomposed. because the microbes need the nitrogen from the soil in order to decompose the straw. How's that? So they need, they're chewing on the straw, but they need some energy there. So anyway, there's another lag here. The previous slide talked about the carbon-nitrogen ratio and immobilization of nitrogen. When the microbes that are decomposing something like rice straw, which has a large amount of carbon but very little nitrogen, microbes need the nitrogen and they take it from the soil water. And you'll see this phenomena advertised in various books and popular magazines. You know, put rice straw in, or wheat straw, something like that, in drainage ditches, or if you have a little pond at your house and you have algae blooms, you can throw straw in, and you know, the microbes extract the nitrogen. And here's a little article right here from 2021 about students from Valencia, Spain, and University of Genoa, and I have no idea how they got a patent, but it says they patented a new technique to eliminate nitrate residue from the water cycle with the help of rice straw. So not sure about that patent, since people have been doing this for decades and decades, but it shows you there are other interests in this also. From a groundwater contamination standpoint, leaching, you can see this is near the bottom left, there's a circle around it. Leaching is the one that various environmental groups are very concerned about. Keep in mind, you can't avoid all leaching from rainwater and from irrigation water. What you can do is minimize it, and often you can minimize it tremendously. And if you minimize the amount of water that leaches out, you also minimize the amount of nitrogen, especially if you have good nitrogen management. So remember that the dominant form of nitrogen in the leaching water, of course, is nitrogen that's in the soil water, which is primarily nitrate. And water has to go below the root zone for this to occur. Finally, there's the fertilizer urea, and we use a lot of different types of urea fertilizer. Just plain urea, UAN32 is the way I normally say it, but urea ammonium nitrate, 32% nitrogen. We have urea sulfuric acid, urea phosphate. Anyway, there are a whole variety of compounds. Remember, urea has no charge in it. It's kind of interesting. So it moves down into the soil with the water when you irrigate, if you're fertigating at that time. But what happens is then it gets down there and it combines with water, and there's an enzyme, the urease enzyme, and it converts it to ammonium. If you see here, 2 ammoniums and then also carbonate. And so that's a process. Again, it's a microbiological process, and it takes some time to occur. So that's the end of this quick view of nitrogen compounds and processes. And it's really meant to be a little introduction, a little explanation, and then to really understand it, obviously, you really have to read the book in a little bit more detail and take your time. With that, I'll sign off and go to the next video.